Hi, and welcome to 12 SDD, Option 2, Lesson 13, Specialty Circuits. Here are the dot points, pause if you'd like to read them. So we're going to look at a number of specially designed circuits that we use in computing, and these are going to be the half adder, the full adder, and the flip-flop. So a half adder is used by a processor to add two numbers together in binary. Let's look at the possible values when we add two numbers. So if we've got 0 plus 0, that equals 0 base 2, and 0 plus 1, 1 base 2, 1 plus 0, 1 base 2, 1 plus 1 will equal 1, 0 base 2. If you look at the rightmost column, that looks like an OR gate. The leftmost column, these would be zeros, and that kind of looks like an AND gate to handle the carry bit. So if we put those two things together, we get an XOR and an AND gate, and a sum and a carry. And so this is the truth table here. So if we have our two inputs for our two numbers, okay, you can see that we output 0, 0, we get a 0 for our sum, 0, 1, we get a 1 for our sum, 1, 0, a 1 for our sum, and 1, 1, we get a 0 for our sum, but we carry the 1, which is exactly what happens when we add numbers in binary. Now the problem occurs when we've already added two numbers together. What do I do with the carry bit? I need to add that, but my full adder, sorry, my half adder can't do that because it's only got two inputs. So I need to add a third one with the carry bit, and that's called a full adder. So here is a circuitry for a full adder. We can see we've got two inputs, A and B, which we had before, but we've also got a third input for the carry in. So this is from the previous circuitry. If you have a carry bit, then it would come in here. And this generally isn't represented by a switch, it's represented as a empty line because that would be connected to the previous circuit. So we've got the XOR and the AND gate here. This is one half adder. We then have an XOR and an AND as the second half adder, and that goes to the sum. And then we have another OR to join the two carriers together. Okay, so we basically combine two half adders and this extra OR gate to make a full adder. And here's a truth table that explains all of that. You'll see this a lot better if you actually make this yourself and have a go, or if you think through the problem yourself and try to think about how you would actually add these together. The other thing we have is a flip-flop, and a flip-flop is used to store a value in memory. And there's a number of different types, and we're going to look at the RS flip-flop. And we'll switch windows. So here's an RS flip-flop. It's called an RS flip-flop because it's reset and set flip-flop. I'm just going to zoom in so you can see a bit better. Okay. So reset and set. And so what a flip-flop does is it basically uses a combination of logic gates to store a value even without power. Okay, so we've got reset and set here. You can see here at the moment that neither of the switches are on, which means there's no power, and it's storing a value. So if I click the set button, then I can see that Q turns on. Q is like my output. Okay, so when it's on, I'm storing a 1, and when it's off, I'm storing a 0. Okay, if I turn set off, it stays on due to the combination of stuff going on here. Okay, if I click reset, Q turns off, so I'm storing now a 0. And again, if I turn set on, I'm now storing a 1, storing a 0, storing a 1, storing a 0. Now, if I have both of them on, I'm storing nothing, and you'll notice that no current actually flows. This is an impossibility as well. You don't want to have two ones on. It just doesn't work. It doesn't do anything. Okay, and so you'll see as soon as I turn one off, I'll store the value that I'm setting here.